Good evening, ladies and gentlemen. For this lecture, last week I showed you some examples and how we worked together with architects, climate engineers, and other consultants. And now today I will show you a little bit more about the special of Machia, about the lightweight structures. Typically, this is a wooden structure, and the structure and the material has an influence to the comfort, to the energy consumption, and to the sustainability. And I will show you some different aspects how to handle this with the material, with the structure, and not to change the structure. First, I will introduce a little bit about the different parameters for building comfort and sustainability. The first is the thermal mass. This is very important to reduce the temperature in summer special, or to have higher temperature in winter without any additional technical equipment. And the thermal mass is also important in summer to reduce the active cooling inside the building. Second will be the insulation. I think typical here is the Japan in Machia to have no insulation or only a little bit insulation. But the insulation is very important for the comfort. It's important for the winter, for the high surface temperature, and this is one important aspect. In summer for the low surface temperature, and with a better surface temperature you can reduce the energy loss in the connective part. One special thing with the contact is evaporative cooling. The evaporative cooling, you can reduce the air temperature very efficiently, and maybe you can reduce the active cooling load, or you have no active cooling load. That's typically the main goal for sustainable buildings, that you have no active cooling systems there. So if you need some energy, especially here is electrical energy, the electrical power, you can use new techniques or other systems, especially the geothermal sources. Sometimes they use it here only for direct cooling, but you can use it also for heating in winter. And you can expand the coefficient of production, for example, with the heat pump. So what is the situation, actual situation with the Machia? What is about the thermal mass? We have a wooden structure, and the wooden structure had a reduced thermal mass. And we had also a very thin layer structure with wooden, so this is one main problem, let's say. We have partially the addo plastering, which is also insufficient thermal mass because the layer is also very thin. We have the windows mainly in a single glazing. With the glass we have no thermal mass, or very reduced thermal mass. And the inner facade is mainly in paper, covered with paper, and also low thermal mass. So, in summary, the thermal mass in the Machia is one main problem. So we can say, if you design a new Machia, you can change the structure. For example, you use a concrete structure. We saw today and yesterday some examples, but this is not, let's say, the old feeling in this building. So the goal, I think the main goal is to use a lightweight structure, mainly in wood, to build it up. What about the insulation? The wooden structure itself had a good thermal insulation, but we have a thin layer, so let's say it's nearly okay. We have endoplastering, it's bad insulation. We have a windows, a single glazing. That's the main problem, because single glaze has a very bad U value, and this is important for the energy consumption and also for the comfort. And we have also low insulation. So that means the main structure and the main material has no thermal mass and no good insulation. The third aspect is evaporative cooling. One special aspect in the courtyard in Macchia is a courtyard, to use it for cooling, but mainly it's used only for visible aspects, to show in the garden we have a few outside and not a few inside. So, but mainly the integration of the courtyard is not good. These three aspects we figured out in the last few days, and this is what we want to work out. What can be the goals? Goals can be aspect of thermal mass to make it better in the same structure. So one possibility can be to use a phase change material as a new material in the construction, called a PCM material. This can be very thin, this is very light, and have a very high thermal mass. Instead of insulation, we have the same problem. Typically, you use let's say, a mineral wool. You need, let's say, 15 up to 20 centimeter of insulation, but this is not in the sense of the structure, of a thin structure. So you have to think about other materials, and one material can be a vacuum insulated panel, VIP. This is very thin and has perfect insulation. The main problem is a window, a self-placed window, and this is a very thin structure, and to find another solution can be to use glazings with aerogel or nanogel filling, or to use also a vacuum double glazing. This is a special product here in Japan, but it has some problems, let's say, with the size of the glass. But can be a good solution. And one goal is to optimize the integration of a ventilation concept to the courtyard and the living space. Natural sources, the goal is to integrate geothermal sources like soil or well, and to use it mainly for direct cooling and together with heating aspect as now I will show you some solutions with real projects. I will start with a thermal mass. And one project is a project in Germany. It's nearly, I think it's nearly 15 years old. It's the site location is in near Frankfurt. It's in Ludwigshafen, and it's a building, an office building. And the goal was for the architect to have a very transparent building. You see it here. And to have a light-weight structure. So this is a part of an office building. This is a heavy structure, a concrete structure, but special the part for meetings and so on should be in a steel structure, but with a high thermal mass. So So what was the solution? The solution was a phase change material. And what does it mean, a phase change material? You need a lot of energy to change a material from, let's say, from a solid to fluid and to gas. And everybody from you knows a very good phase change material, it's water. Water is a perfect change material. But water has its phase change not, let's say, the room temperature of 26 degrees. This is, let's say, the main temperature in summer. So water changes from solid to fluid by 5 degrees, nearly 5 degrees, and from fluid to gas 100 degrees. So it's not possible to use water as a phase change material. But there is a lot of energy inside. For example, to melt water, you need the same energy as you heat it up from 0 to 80 degrees. That's very important. So, for example, we have a lot of water in the air. You see it something like a cloud, and the water stores a lot of energy. If we have no water in our atmosphere, we have temperature differences from day to night from, let's say, 200 degrees. So the water, the latent energy is very important to save energy and to reduce the temperature difference. So another material can be, it's called paraffin. You use it for a candle, for example. That means it has no good fire protection, but you can see it here. This is a comparison between concrete structure, ceiling with a thickness of 25 centimeters, and paraffin with a thickness of 2.3 centimeters has the same capacity. And paraffin is very light. So that was the goal to say. You see it here. This is a micro-absorbed paraffin. And the goal, this is a simple system. The goal is to use it nearly the same as concrete. By night, you cool it out, for example, with a cooling tower, and you have water pipes inside the structure. So that means the water cooled down by the air from outside and cooled down the paraffin from solid to from fluid to solid. And by day, it's an absolutely passive system. The construction stores the energy and makes the step from solid back to fluid, and needs a lot of energy. And the energy will come from the air. So that you see it here, we have by night 15 degrees outside and day 32 degrees, and inside the building we can achieve, let's say, 28, 26 degrees with a light white material. This was a prototype. You see it here, this is aluminium coupled system. Here you see the gypsum with the PCM. You need the gypsum for the fire protection. And you can see also here the water pipes inside. This is a very simple system. You see it here, filled with gypsum. And you can imagine you need only 2 persons to build it up under the roof. It's a simple steel structure with the PCM panels under the ceiling. That was the result. Complete steel structure, artificial light integrated, and also a top light integrated. A very light structure, but a very heavy mass. The next is nearly the same. It is a residential house in Munich. It's a residential house for 4 people, nearly 200 square meter total area. You see here the main house and some smaller houses beside the main house. And this is also a steel and wooden structure. And here we did it only by air, the recovering of a PCM material. We have PCM ceiling, also walls of PCM, and we did by night flushing, 15 degrees or let's say 70 degrees. We cooled it out, and by day we had the same passive system as we saw before with the material. You can buy it. You see it here. It's called micronal. This is a gypsum board with a PCM, but we need, let's say, to have a good thermal mass. We need minimum 3 panels. So that means in the end, it's also a little bit heavy, but mainly you have also the problem with fire protection from building to building. That means you need additionally 3 boards. Another solution can be hydroxide salt mixture. The advantage from this system is that you have no problem with fire. It's absolute fire protected, and the capacity is much more higher as a paraffin. So you can use it for example, to fill up some structures, for example, the roof structure. It's also possible to use it here, for example. And yeah, it's very easy to implement it in the structure. So this is very common technique in Europe for these lightweight structures. A development can be, for example, to use it also in glass structures. You can see it here. It's a little bit translucent, and the advantage is you can save, for example, the solar energy direct in the facade. So it means we have here a very heavy, thermal heavy structure. That means we have no solar energy, solar loads inside the building. This is very, I think, also interested in the architectural aspect to use translucent elements in the facade. And I think for Machia they will use translucent papers or translucent glass elements. I think we can combine it very good in these structures. Okay, that was the thermal mass. Another thing is insulation, and to understand how it works, you have to know something about the basics, about the U value. The heat transfer has 3 different mechanisms. The first is the conduction. It depends on the material and the thickness of the material. The other is the convection, which depends on the surface temperature. And the third one is the radiation. This depends on the material emissivity. Last week I showed you the project from Bangkok with the low heat coating. This is the effect of the low emissivity of the material. So these all together, the resistance of the convection, the resistance of the radiation, and the resistance of the conductivity, this depends on the thickness of the material and the lambda of the material, is the U value. And the goal is to have a very low U value. typically in Germany you have to fulfill a U value lower than 0.28 watt per square meters in Kelvin or more, for example. So how can we achieve this in a very thin structure? Typically you can use a polyurethane panel, and if we use, for example, only 5 millimeters with a thin structure, we have a U value of 2.8 watt per square meter in Kelvin. This is a factor 10 higher as in Germany. I said 0.28 is the minimum, the maximum of a U value. So we have to reduce it, but we cannot expand the thickness of the material. One solution can be, for example, the vacuum insulation panel. And if you use, for example, a 5 millimeter panel, you can reduce the U value from 2.8 to 1.1 watt per square meter in Kelvin. This is a common U value for a heat mirror glazing in Germany. So that means we are in the same range of U values, without any change of the structure of the machine. How does it work? I think everybody from you knows it. This is a double walled vessel, and between the two walls there is a vacuum. That means we have no conductivity and no convection inside, and we have a very good insulation. This is the same concept with a VIP panel, and the construction is very easy. We have a core, a microporous core with crushed silica. We have fleece to cover the core, and outside we have aluminium covered foil, because we have to take care about the humidity of the air. Because if we have humidity inside the construction, we have water inside, and water has a good energy transport. So this will reduce the U value of a system. The typical thickness is 60 millimeters. It's the same as double glazing, but you can use it also very thin as 5 millimeters or 3 millimeters. You can find it also on the backside of a refrigerator. There is a recooler, the heat exchanger, and between the heat exchanger and the refrigerator you have also a VIP panel, typically. This is a photo how you can use it in the construction. Typically we have a wooden construction, we have under construction. Between this construction you can implement this panel. Very simple. So this is how we can handle the opaque wall. And the other is the transparent part. So we start with the single glaze, and the single glaze, you can see it here, have a U value nearly 5.8 watt per square meter in Kelvin. That means a very high U value. That's the problem. It's nearly only the part of the convection and the radiation inside and outside, because glass at a very high lambda, 5.81. And to optimize it, the first step is to make 2 glass layers. This is a double glaze. So it means we can reduce the convection and the radiation to the outside, and we can reduce the U value by half from 5.8 to 2.8 up to 3.0. I think this is common here now in Japan to use double glazing system. And to reduce it more, we have to use a low E coating inside the layers. That means we have, this is the inner glazing, this is the outer glazing, and on the outer surface of inner glazing, typically there is the low E coating. This is a metallic coating, and this reduces the radiation from the inner surface, from the inner glass layer to the outer glass layer. And there we can achieve a U value nearly 2.0 watt per square meter and Kelvin. And the next step is typically to use a gas-filled system. Typically it's argon. And with this gas filling, we have a typical U value nearly 1.3 watt per square meter Kelvin. So the step from a single glaze to a heat mirror glazing is from 5.8 to 1.3 watt per square meter Kelvin. And this is the same range as a 5 millimeter VIP pen. Now the solution can be instead of a gas filling, because gas is very expensive, we can use also a filling with a silica aerogel system. You can see here, this is a translucent system, this is not transparent, but also with a special facade, paper facade of Machia, this can be also a good solution to use this system. The U value is better as a gas filling. You see it here. Gas filling system has a lambda of 0.025, and we have here 0.018. This is nearly the same as argon, and it's much more cheaper. Point is that with aerogel, you fix the gas molecules of the air, and that means you reduce the conductivity of the air. And if you use this nanogel or aerogel filling, for example, with a 10 millimeter glass system, we can achieve also a U value nearly 1.4 watt per square meter Kelvin. That means nearly the same as a gas-filled system, but only with the thickness of 10 millimeters. So, that can be used also in this old structure. Typically, these are sliding elements. So, last but not least, the vacuum glazing is also, I think, a very good solution. This is a special product here in Japan. You can achieve U values nearly 1.2 with a glass size of 6 up to 10 millimeters. Also, you can see here a section of the glass. We have 2 layers. We have functional glass spaces between, because we have a vacuum inside and we need the spaces to achieve a gap inside, and we have a gas-proof glass composite outside to fix both layers. If you have a near view to the glass, you see the close range effect of the dots here. But in the practice, this is not a problem. You can't see. The problem of the system is the composite at the edge of a glass, because here we have only a glass structure. That means we have a very high conductivity, and you can see here. This is a simulation. Red means that it's very warm inside, blue means it's very cold. That means we have a very high energy transport at the edge of a glass structure. That means in the end you need a good frame insulation of this glass. This can be a good solution. Typically you have a restriction with the glass size. I think the size of 2.50 meters to 1.50 meters is the best one. Last week I showed you this slide, how to work in the project. You can imagine you have 3 steps. The first is to reduce the energy consumption, the third is to maximize the efficiency, and the third step is to use renewable energy. And I showed you also very short this building. This is our smallest building, 6 square meters. And the goal was here to design a complete energy autark building. That means you have no connection to the energy grid, no electrical power, no water, and so on. And the result is a very complex building. So that means you have a lot of layers. You can see inside the wooden structure we have vacuum insulation panels around the wooden structure. Outside we have aluminum covered surface. We have a separation composite toilet. We have an air-to-air heat pump system. We have a ventilation unit. And all together makes it comfortable and dependable. I think you can imagine that the work, the design work for this project is very important, and it's also important the discussion between architects, engineers, and structural engineers. From the first view, it's a very simple building. It looks like a garden, small building. You see the wooden structure, the aluminum covered surface. You see the solar panels. You see the thermal collectors, solar thermal collectors for hot water. This is for electrical power. This is the south side view. On the north side we have a storage tank, a water storage tank. We have a window to the north side because south side in summer is too hot. North side is much more better. We have small windows to the south side. The door, you can see here also a water storage tank. This is an inside picture. This is a bed. You can grab it here, right there. And you can buy it. I think nearly 50,000 euros you can buy it by Volkmar. And last week we discussed also about the comfort, about evaporation cooling, and in respect of the courtyards in the Nachia, there are a lot of potential to use this cooling effect. And to show what is the potential, I will talk a little bit about a project, a running project in Singapore. It's an outdoor comfort project, and it's called the Elephant Walk. This is a walk through the forest in Singapore, and sometimes it's very hot and very windy. So, and the major came to us and said, we need a solution that we can achieve a good comfort walking through the forest. And that was the same question as last week I showed you what is the outdoor comfort. and especially for outdoor comfort, there is a special, let's say, system to evaluate it, because UTCI is nearly the same as a perceived temperature. And what we learned is that outside the temperature below 32 degrees, it's a moderate heat stress, so you can say under 32 degrees in a hot and humid climate, it's okay to walk there. And what we did, we made a test with persons walking there. First we measured the temperature, the UTCI, and 32 degrees is okay, lower than 32 degrees. We measured on direct in the sun, and you can see here the UTCI nearly 37 degrees. And here you can see the range. Yellow is okay, red is not okay. That means all in yellow or green is good. And if you take a look there, you see also the humidity there. I can't see it here on mine. So 60% humidity, and you can see it's dry, 60% is okay, but it's not comfortable. It's not comfortable. Then you change the street, you go to the shade, and you see the UTCI reduced to 33 degrees. It's better, but it's not 32 degrees, lower than 32 degrees. And the humidity grows up because it's colder. Then we made a test. This is a walk, and we used different ventilators and different water nozzles, and there we made evaporative cooling. And you can see this is a measure point here, 33.5 degrees. It's worse than before. Why it's worse? Because the wind speed is lower. It's here calm, and here we have the wind speed, we have the breeze there, and it's better. So that means the influence of the humidity, the wind speed, and the direct radiation is important for the comfort. So when we measured direct in the middle between the different ventilators, and you can see we have an elevated air speed nearly 3 meters per second, and we have a humidity of 95%, and we have UTCI of 28 degrees. So that means we have a high humidity, but everybody will say it's perfect there. Everybody. And if you measure it direct in front of the nostrils, we have a humidity of nearly 98% and it would be 26 degrees. That's absolute perfect. And the mayor asked us, is this really comfortable? 98% relative humidity. And we tested it. We make it open for the visitors, and we make a movie and some pictures, and it was absolutely incredible. Everybody stand in front direct of the nozzles of the fans nearly 10-20 minutes, and they love it. This mother with the children stands 50 minutes in front of the nozzle, 50 minutes. And that was the sign for us that this is absolute comfort. So that means the potential with the courtyards in our Machia is very good for the climate inside the courtyard. That's very good. And this can help us to reduce the temperature inside the building. It's very amazing. The children had a lot of fun there. So, the question is how we can implement it in our courtyard. And this is a very old traditional system to use a courtyard for cooling down the building. You can see here this is typical in Arabic world, in Persia, the wind towers, the wind catchers there. And this is a typical situation. You see the wind towers, you see the courtyard, you see water there, and you catch the wind with the wind towers, bring it down, you evaporate it with the water and cool down the rooms under the ceiling. This is a very old simple system, and we used it also for a school in Damascus. The goal was also there to have a good inside comfort without any cooling system, active cooling system. And we made it very simple. Together with the architects, there was a competition, we won the competition, and the first was to analyze the situation. We did it also here with our project, and what we saw is the temperature are really moderate. We have temperatures sometimes between 38 and 40 degrees, but mainly about 35 degrees. In winter it's not so cold. I think it's nearly the same here in Kyoto, but it's very arid. No humidity. And the architectural response you can see here, we have a very heavy structure, only stone structure. We have wind towers. That means we have a very good thermal mass, and so we can balance the temperatures between day and night. And it's also typical is the courtyard, the using of the courtyard is a little bit different to Japan. The courtyard there is a place you can meet together, you can eat something and so on, where you will stay. And this is the project. You see here the open courtyards, open to one side, the trees inside, and here the turnaround areas between the different building parts. And this is the main concept. This is one classroom or one house with two floors, two classrooms. And this is a very simple concept. We have a courtyard here, we have evaporated cooling here, and we use this one to cool down the air. We use also earth tubes or earth pipes and use the soil temperature to reduce the temperature additionally. We can use it also here very good because we learned that the temperature is nearly 16 degrees here in depth of 8 to 10 meters. That's a very good potential. And where the air blowing inside the building has a temperature, let's say, from outside 35 degrees, inside 22, 25 degrees. And together with the thermal mass, it's absolutely comfortable. The question is, how we can transport the air inside the building. You can use a fan or a ventilator, but you can use also a solar chimney, and we use the wind towers not to catch the wind, we use wind towers to use it for a solar chimney, to use it for the exhaust air. And with a special construction you can use the wind speed to support the air outside the building, because it's under pressure. That means the wind produces under pressure and sucks out the air. We have a thermal mass sphere, a ceiling. We have fixed shading elements, same as here with the machias. And in the first time we used an additional movable shading device because the trees are very little at the beginning. But this is a concept with no heating elements, because with the soil in winter we heat up the air and we have no problem. can see here the winter day, we use also the sun for heat up the air, and if you have a heated up air, hotter air there, you have a very good chimney effect. The fresh air comes via the tubes inside the different rooms, heated up, and goes out. In the summer we use the courtyards, the trees, the water to evaporate the air. We use the tubes to cool it down, and in the summer it's very important to have the solar chimney because typically in summer the air outside is hotter than inside, so that means if you have no ventilator, the air don't want to go out. In winter it's perfect because outside it's colder, but in summer it's not possible, so you need here a part of a chimney should be hotter than inside, hotter than outside, so that means now it's the same as in winter, the air is hotter, so the air goes out. Very simple system. If you use this passive system in summer, you have to achieve that by night you have to recool the thermal mass. So that means in summer night it's very important to do a night flushing by the windows and also to recool the pipes in the soil. And with both systems, day and night, we can achieve the comfort. With the fixed shading elements and with the small windows, then it's also important to check the daylight situation inside. In the first step we had only windows to one side, to this side, and we find out that on the other side it was too dark. The result was that on the other side we designed also some small windows to have a good daylight situation inside. That's important in the design of the building. The other thing is the thermal optimization, but the other one is the daylight optimization. Both together is to find out the best compromise between both. So, what is the result, the thermal result? You can see here one hot day, we have temperature here 35 degrees outside temperature, and you can see the different variants of the system. The brown line is the ambient temperature, the orange line is the temperature with only night flushing air change rate of 2. You can see we have temperature nearly 40 degrees. The second was we use a microclimate of the courtyards, then we reduce the temperature nearly of 1 degree. The third was then to have a better night ventilation. So we reduce the temperature nearly 30 degrees, 31 degrees, and with all together, all measured together, we had the temperature nearly 40 degrees. And with a comfort range in Damascus, it was absolutely perfect. You can see some pictures of the solar towers. Here is wind supported. Here is a glass structure. On the back side it's flat to have high absorbance, to have a high temperature. You can see the courtyard. And here is also a picture of the courtyard. And here are the openings for the fresh air connection to the tubes. Here is the more trees and the movable shades. So now we heard about some different measures to optimize the comfort, to reduce energy consumption. And I show you very short a project. This is a project from our university, the solar decathlon. I think Jan Kremers, who will be here tomorrow for 2 weeks, will explain it a little bit more in detail. But in this project you can see all different elements being combined here. The solar decathlon is a competition between universities. This is in the States and also in Europe. This was the first in Europe, 2010 in Madrid. And it's a solar decathlon with 10 different disciplines. You can see here the amount of how to compare it between the different disciplines. You see, architecture is very important. Also, energy is important, up to innovation and so on. Total points are nearly 1,000 points. In the end, the first 3 places we had, the third place, the difference, I think, 6 points. So, I think it's for all of it. You can see here impression of the building, and what is mainly clear is we use a lot of photovoltaics there, of different photovoltaics. We use a wind tower for natural ventilation and for natural cooling. And we use a light structure. It was also a wooden structure because one goal was to build it up in 1 week. You have to transport it there and you have to build it up in 1 week. So it was not possible to use, for example, concrete or another material. So wood was the only material. So it means the first step is the wooden structure. The second was the insulation of the building. Then we covered it with an active component with solar panels to produce the energy. Then the next step was to make some climate gaps for natural ventilation and also for daylight. And here you can see the different modules, so it's possible to use more modules behind, so you can expand here. Here's a ground floor. You see the entrance there, you see the bedroom, dining room, living room, and the gaps with openings for light flushing and cross ventilation. This is a section. Here you can see the ventilation tower, the solar chimney. You see here the thermal storage, it's water and salt storage. And this is a view to the different solar modules. You can see here the typical PV modules. Here is a special module, it's called a PVT. This is a combination of a solar panel, of a PV panel, and a thermal panel. Behind the structure there is a water piping system. And with the water piping system we can use this one for recool the phase change material inside the structure by night, only by a passive system. And you can see here the ventilation power. It's nearly the same as I showed you in Damascus. We have a gas tower with the solar radiation, with a high temperature in summer. We have opening for the fresh air, and we have evaporation part here. And there we can bring in a very cold, fresh air. And with the active and passive system for the PCM material, by day we have an active system. That means we produce here electrical power with the PV element, and we run a chiller, and with the chiller we cool down the PCM material. And by night we use the PVT element how passive recool the phase change material inside the room. It's a combination of both active and passive components. So you can see here the typical photovoltaics, the PVT, and here is additional a vacuum solar tube for hot water. This is also important for reactivate the salt storage under the building. This is a complex system. I think Jan Kremers will explain it a little bit more in detail. The result is very easy. You can see the temperature for 1 year, and we can reduce by active and passive components the maximum temperatures, and in winter we can heat it up in a band, let's say, between 26 and 20 degrees. And the goal was also to produce or to use only the energy that you can produce by the building itself, without any connection to the grid. These are some impressions of the building. Yeah, the solar decathlon is, let's say, it's a competition with different aspects. And in Madrid, there was some teams from China, some teams from South America, and their budget for their buildings, I think it was 100,000 euros. Our budget for our building was 1.4 million euros. So it's nearly a competition between a bicycle and a Formula One car. So I think that I think they did it also. They have to think about, is this the right way to make a competition? I think it's a better way to make it more in a passive context, to say how can we make it passive for especially for winter better and without any energy consumption. I think that's more realistic. Okay, what are the conclusions now for our Machia? It's a little summary. For thermal mass, we use a wood structure with phase change material. We can use it, for example, in the fixed boards. We can use it in the sliding doors, in the opaque parts. We can use it, for example, in the ceiling under the wooden construction, and we can cover it also with a wooden system. We can use different insulations in the opaque part, in the outer facade, the vacuum system. For the translucent paper elements or glass elements, we can use the aerogel glazing or the EIP glazing or the typical liquid glazing. For the evaporative cooling, we should use a courtyard with an optimized ventilation concept, maybe with combination of a solar wind tower. We should optimize the evaporation with the plants. It's very important to have flowing water surfaces. And we should use natural resources implementation, especially for geothermal source. The tubes, for example, or the heat pumps, or the direct cooling. In the end, you can see a very simple concept sketched for the Machia. We see here the courtyard, we see here the water parts, the tubes. You can cool it down in the summer with the solar chimney. We have natural ventilation there. We can use the heat pump together with the soil or with a well to heat up a building with a wall system or with a floor system. Yeah, and we have to use good insulation of the walls and also of the walls. So that's all.
you very much, Professor Bleicher. I understand the general condition of our material. There are also good diagram which optimize all the stuff in present situation. So, yeah, thank you very much for nice presentation.
Are there some questions? Hopefully. If not, I will make a test with you to calculate the U value. So, please make some questions.
Could you go back to the section of ventilation tower?
Of the Damascus project?
Yes, this one.
Of this one?
No, you have a section of the fifth.
Okay.
Could you go over it?
This?
Could you explain?
You explain, okay. It's the same concept as wind towers in Damascus, yeah, or in Arabic area. You have a wind speed here normally in 10 meters high. You have no problem with the wind speed. On the ground floor, you have a resistance of trees and so on. That means the wind speed is very low. So you can catch the wind there with the main wind direction, and you have openings there. So that means you have a pressure on the facade. So the wind will come inside, and here we have an evaporative element. In this case, we have a mesh, a metal mesh with water. You bring inside water. And the water goes down, and the water evaporates the air. So that means the air has a temperature, let's say, 32 degrees and a humidity of 60%. And here the air has a temperature of, let's say, 25% and a humidity of 90%. So that means we use the evaporated adiabatic cooling to cool down the fresh air. That means we don't heat up the building inside with the hot air, because we need air for the people. Yeah. It's in summer. If you're in summer near of small water area, there is always colder as far away from the water.
So you need also, in addition, openings in the facade, of course.
Yeah, you need openings. Yeah.
Where are these openings?
Here, in this case, the openings are the gaps between the different modules. There we have the openings.
So is it just a gap, or is it?
Yeah, here it's a gap with operable windows. You see here, it's lamellas. It's two-layered facade. Inside we have insulated facade. Here is a single glass facade, and we have openings, windows we can open, so the air can see inside and goes out there. Typically, we open the windows on the other side of the wind direction.
But it can be very tricky. It depends on the pressure you have.
Yeah.
If the pressure is low, you need very small openings. If the pressure is higher. So how is there a regulation?
There's a regulation, yeah. Typically, there's a regulation.
Controlling with the electric.
Yeah. Behind the very simple building is a very high-tech control system. That's clear. And also a high-tech active system, because you need heat pump combined with water, salt water storage, and so on. And the load and discharge system, this is very tricky.
So, in case of much house, so is there a more simple way to?
Yeah. Then I think we can open on different sides only by hand, and we have very, let's say, a very wide openings to the gardens, and then we have no problem. The problem here is to the energy consumption. It means we have to fulfill that we can only use the energy that we can produce on site. On the Machial, we have not the problem that you have to fill this.
So the courtyard will help us in different ways.
Absolutely, the courtyard helps. Absolutely. If we combine it better as in the situation now, to connection to the building, it helps us very much.
So we had an internal discussion about problems with mosquitoes and little creatures.
Yeah.
Very a nuisance. So
yeah, we have to think about different openings covered with a mosquito mesh, for example, or we can cover the part of the courtyard in horizontal at the roof, for example. I think there will be some different solutions. I think it's mainly in different months, it's not the whole year with the problem with mosquitoes. So we can make a system, we can build up or change it. I think the goal is to design a very simple system, not a hybrid.
It's not a question, it's more like a comment. I think it's an amazing presentation you give on the abilities of highly technological new materials. Like you can apparently make two sheets of glass that are very thin and with vacuum inside, and you have an amazing insulation with a very thin piece of glass. But I think that bringing it into a traditional Japanese house raises for me a pile of aesthetic questions. And I'm thinking that the tactility and the sort of the presence of these new materials are very, very different from the materials that the original house was made of. So perhaps one should consider not replacing materials in the old house, but rather install new materials in a completely different layer in the building, like adding something that was visually clearly added, a very modern thing to do.
But the goal was different. The goal is not to change and not to change the structure, not to change the architectural aspect. Because the thin layers, you don't see it, the thin layer, because it's covered with the same material. For example, the vacuum glass, it has the same thickness as your old construction, so you see no difference. It will be different if you say, for example, you use a triple glazing system with a size of 29 millimeters. That's the idea, and also the VIP vacuum isolation system, it is covered between the two wooden layers. So in the end, you see only.
Okay.
That's it. That's important. You see only a little bit that, for example, this structure has not, in this case, let's say 50 millimeters. In the end, it's only 5 millimeters you can see of this wooden structure. But you have the same structure. If you use typical materials as an insulation material, you need both structure. Maybe it's completely different, but the depth of a system is nearly the same. That's the goal of these materials, not to change it. If we will change the architecture here, we can use different materials because this is completely different structure. That's the goal of these materials. In the end, you come in the building and say, okay, this is a match as I know, and only in very, very detail you see, okay, the distance is a little bit low. In Germany, it's very easy. In Germany, the engineer will come and say, we will make a insulation 30 centimeters, and we have no problem with the energy and the architecture. That's not so important. But that's not the goal here.
For me, it's also it's a feeling. They say to me, "Is it really right?" So keep in mind, this high-tech materials with the traditional building. I don't have a final decision. So because of course you need working with a VIP panel. If there's just one name, or if you're not absolutely careful, that you penetrate it and it's done. It works.
Yeah,
It doesn't work anymore. So it's very, very tricky, and all the little things to bring it together. It sounds quite easy, but I'm not sure whether it's so easy. So I think it may be a way, but I think it's a process, focusing on the details.
Yeah, I think that's a realistic discussion. You're absolutely right. In the end, if the result is that you can't use new materials with the old material, this is also an result. But on the other side, you can say the question: the designers, the architects, who started with the material, with the structure and with the materials, they have not the possibility to use different materials. I think if you are an architect and you have now the possibility to use different materials, you never will use the old materials because they are not so efficient. I'm sure that the old architects use also in the same time the best materials they had. So they have never the possibilities to say, I want to use this plastering, or I can use a VIP system. They have never a chance to do it. So the question is this so important? But yeah, this is a discussion. It's true. Yeah. I think let's say in 50 years, we have other materials, much more better as a VIP. And I think then we have the same discussion. The architect will ask us why we don't use the new materials because the VIP is important for the architecture and so on. But we had no possibility to use a better material. I think that's a progress of architecture and materials. But I think it's absolutely right to discuss architecture together with materials, with sustainability, with comfort and so on. This is a floating discussion. That's a very important floating discussion. You have to say, no, this is our architecture and we use this material for every time. That's my opinion.
I think it's convincing that the passive system, it's just an improvement of the passive system. If you love your house, you used to live it, and oh God, I'm freezing in winter, and it's always too hot in summer. So with this expectation, maybe it's a good balance to have comfort, to use energy, and to keep the character of the house. And if they are, steps with prototypes, that it really works and how it looks like, then perhaps it's a realistic solution.
Yeah, I think the architecture is very important. But I think how you can handle it is quite different. I think a good example is the computer. Today, I think nobody from you knows what is the processor inside, what is the storage capacity, and so on. At the starting point of the computers, I know it was very important to have the best processor. Yeah? Everybody talked about, I have this processor. Today, nobody talks about the processor, nobody, because it's clear this is a good processor. And I think we in a discussion in architecture with new materials, we in the same discussion if I have this processor or I have this material. I think in 20, 30 years nobody will talk about it. We have a very good material to fulfill our requirements for architecture and sustainability. And it makes no difference if there is a VIP system there or another system. This is an absolute different step to architecture.
In this material, available all over the world. Yeah. So I never this material in Japan. It's paraffin.
Yes, paraffin. And it's not possible to buy it. You can import it from Europe.
Yes, yeah.
It's like cheap.
Yeah, I will be amazed.
Yeah.
The result.
I think the most difficult part for Japanese students, or for even for me, is to accept or convince your theory or your idea is you convince that thermal mass is you contribute to the comfort.
Yeah.
So, but in Japanese traditional idea, I mean, there's still, I mean, you said it's light structure, but heavy or massive thermal. But maybe in this semi-tropical climate, we have kind of traditional idea to pursue a lightweight in every context. So so many Japanese students have come out for a model of like that bridge, or you said double wall vessel. So it's depending on the insulation. But in tradition, for instance, traditional Japanese model, it's basically depending on ventilation. So it's with more importance on movement of the air. For instance, you ignore the fact of vaporization in courtyard, but in traditional courtyard, that is because we didn't have glass. So that is a kind of the core is to provoke what we call air movement by spreading water. So because this is a bowl, it's geographically wind speed is very low.
Yeah.
So we have to provoke it by ourselves. So that's kind of more let's say dynamic system, depending on the movement of the air itself, rather than still air condition. So that's the biggest difference, or the biggest turning point, or critical point to pursue the let's say technology or all kinds of things. Technology is important, but direction is very important. What to pursue. So I expect the engineers more. I personally expect more to engineers to have a kind of dynamic analysis, which is now possible with a computer. We have more capacity to analyze and dynamic situation. So what I expect to you engineers. How do you think about the difference of the basic model?
Yeah, but in the end, there is no one solution for the buildings. There is
That's
no
true.
one
That's
solution.
true.
It depends on the side, on
That's
different parameters. And the step is always to come from a passive system. This, you can optimize the passive system, and you have those possibilities to save energy, to comfort. This is the first step. If you have, for example, a building with a lot of people inside, an office building, yeah, and you have a restriction about the humidity and so on, a passive system cannot fulfill it. So that means you have to change to an active system. And if you change to an active system, you have to analyze or to prove, make the passive system, in this case, makes it sense. So in the end, it's always an optimization between the different building types and so on.
Yeah.
And nowadays, you can optimize it by computer.
Yes, that's what I mean. Because in let's say 80s, all office buildings are switching cooling system by the end of let's say September. From the 1st of October, they switch on the heating system. So because it was impossible to connect or analyze the connected situation with open system, local system.
Yeah,
But because of the technology, now we can analyze and
you can do it today. But in the end, it's a question of energy consumption and energy production. If there's, for example, a very fast system, a ventilation system, air cooling system, you have to produce energy directly when you use it. So if a massive system, you can use a night flushing system.
that's
And by that you don't need an active system. But if you have different restrictions about temperature and so on, sometimes you have to shift to an active system. And the combination of both sometimes makes sense. But we have also, for example, buildings with only active systems and no passive system. Yeah? Because in this case, it makes no sense. And in the end, I said it before, it's always a discussion between architects and engineers to find out the best compromise between the different disciplines. That's it. The goal here was to show what are the possibilities with new materials today. And the next step, our students will do it in the workshop, is to prove it makes this sense. In the end, it makes no sense and it makes no sense. Yeah? But I think different aspects can be helpful to think about with new materials to save the old structure.